All right. A Bernoulli process. A Bernoulli process is an experiment that consists of repeated trials. Experiment consists of repeated trials of The outcome is either a success or a failure for each trial. The outcome for each trial is either a success or failure. So this is sort of binary. There's no in between. There's no third option. It's either a success or a failure. All right. The success probability remains constant throughout each of the trials. The success probability, usually a lowercase p, remains constant. So this does not change. Remains constant, and all the trials are independent. That is a Bernoulli process. And this is actually a pretty common type of process to encounter, a pretty common type of experiment. We have some repeated experiment, and we define success in some way, and everything else is a failure. So a quick example is, say, rolling a standard 6-sided die. And we could define a success as getting, for example, rolling a 6 as a success. Everything else would be a failure. Well, every time we roll the die, we know the die rolls are independent. The probability of getting a 6 stays the same. That's 1/6 on every die roll. Okay, and we can repeat this over and over and over again for as many trials as we would like. So oftentimes what we'll do then is we'll count the total number of successes in a Bernoulli process, right? Say you're going to roll the die 9 times. How many 6s do we get? When you count the total number of successes, we get a specific type of random variable. So if x is counting the total number of successes, in a Bernoulli process, that is called a binomial random variable. Binomial random variable. A binomial random variable counts the number of successes that you have in a Bernoulli process. And let's go ahead and write out a definition here. In a Bernoulli process, with n independent trials, and with the probability of success being p, probability of success is p, and failure probability, we tend to use the letter q for failure in a binomial random variable. Success probability p, failure probability q. If p is a success and there's only 2 outcomes, success or failure, then q must be 1 minus p, right? So we can use p and 1 minus p, or p and q. The random variable, capital X, denoting the total number of successes in these n trials follows a binomial distribution. In these n trials follows a binomial distribution. And the binomial distribution, the probability that x takes on a value little x, a binomial distribution, this is a function of a few things. A lot of books, a lot of texts will denote this with a little b, lowercase b, with n trials and success probability p. These are the two parameters that you need here. You need to know how many trials, and you need to know your success probability p. This is equal to n choose x times p to the x times q to the n minus x. That is the probability of getting exactly x successes in n trials. Or we can write this as n choose x, p to the x, instead of q, we can obviously write that as 1 minus p, right? To the n minus x. This is our probability distribution. This is good for x. You can have 0 successes, 1 success, 2 successes, all the way up to n successes. All the way up to n successes. Okay. I'll also mention here that the mean, the expected value of the number of successes, is n times p, and the variance is npq. npq. That is the binomial distribution. Okay. So before we dive into some examples of trying to use this, I want us to talk specifically about the PDF. Let's try to do a little bit of an, maybe a little bit of an explanation of the terms in your binomial distribution. Remember, x is counting the number of successes. X is counting the number of successes, all right? So how is this going to work out? Well, consider a specific sequence of x successes. Consider a specific sequence of x successes. If you have n trials, then there are n minus x failures, right? If we have n trials and there's x successes, there's n minus x failures. So a specific sequence, let's say we have success, success, success. Let's say we get all successes up front, and then we have failure, failure, and then a failure, right? So there's x of these s's, x successes, and then the remaining are failures. So there's n minus x failures here, right? Okay, so what's the probability of this specific outcome? What's the probability of this specific outcome, right? Well, the probability then of getting the success, 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 yada, 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 success, failure, failure, yada, 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 failure, because of independence, because these are independent, if this is a Bernoulli process, these are independent, the probability of all of these events happening at once, or the intersection of all of these, getting a success in the first trial, success in the second, is just the individual probabilities because of independence. We can split that up, right? Yada, yada, yada. Okay. And then times the probability of a failure, yada, 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 times the probability of a failure, right? Well, if the probability of success doesn't change, and there are x of these success probabilities and n minus x of these, this is just going to be equal to p times p times p times p, and then times q, yada, 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 times q. And there's x of them, so that's going to be p to the x power, and then q to the n minus x power. All right. Now, this is only for this specific sequence of x successes. So what's the probability of any sequence of getting x successes? Well, you can reorder these terms in sort of any way you want. You have n different trials, and you need to choose x of them to be success. That explains the combination term n choose x, right? There's n trials. We get to pick x of them to be success. Since the total number of ways to get x successes in n trials, total number, just counting the number of ways, there's n trials, choose x of them to be success. For each of those, the probability of getting that would be p to the x times q to the n minus x. Probability of there being x successes then is n choose x, choose your trials there, p to the x, q to the n minus x. And we get our binomial distribution. Okay? I much rather want us to think about this in an intuitive way, rather than trying to sort of like memorize formulas, because at the end of the day, when you're not doing examples in a video section titled binomial distribution, you have to identify that it's a binomial distribution. And so you want to look for these characteristics. You want to look for the idea of there being a fixed number of trials and counting the number of successes. And you want to identify that the success probability p isn't changing, and things like that. Okay. Now the mean of the binomial distribution is n times p, and the variance is npq. I'm not going to go over proofs of those. I think some of those are relatively intuitive. If your success probability is p, and you do n trials, well, on average, how many of those trials should be a success? Well, p times n, right? I think that makes some sense. Let's take a look at an example before we close this one up, and then I think maybe we'll get a better intuitive idea of the binomial distribution. Let's see. The probability that a certain kind of component will survive a shock test is known to be 3/4. Assuming independence, find the probability that exactly 2 of the next 4 tested survive. Find the probability that exactly 2 of the next 4 tested survive. Probability a certain kind of component will survive a shock test is 3/4. They are independent tests. We're going to do 4 tests. What's the probability that exactly 2 of the next 4 will survive? So in this case we have n equals 4 trials, and a success probability is 3/4, right? What's a success in this example? A success in this example is surviving a test, right? That's 3/4. So p is 3/4. Q would be then 1 minus p. Q would be 1/4. So what's the probability that exactly 2 of the next 4 survive? The probability that x is equal to 2. What is the probability that x is equal to 2? They are independent trials. This is a binomial distribution. We're looking for 2 successes out of 4 trials. with success probability 3/4, where you can plug it into the binomial distribution, or think of it intuitively. There are 4 trials. You need 2 of them to be successes. So out of the 4, choose 2 to be successes. For each of those successes, they have a probability of 3/4. You get 2 of those. So because of independence, we can multiply the probabilities together. That means there's 2 failures out of the 4. So a 1/4 probability for each failure squared. And then we just need to multiply everything out. So we have 4 choose 2, which is 6, I believe. 6 times 9/16 times 1/16, and that is 27 over 128 after we reduce down there. Right. That looks good. Okay, so there's a binomial distribution. What's the probability exactly? 2 of the next 4 tested survive. 27 out of 128. All right. I'll mention just a little bit of extra here. Just note that the mean, right? The mean is, remember, the mean is n times p here. So that would be 4 times 3/4. If the success probability is 3/4 and you test 4, on average, what's the expected number of successes to get? The expected number of successes then would be 3. So the mean would be 3. And the variance would be NPQ. The variance would be NPQ. Well, we know n times p is 3. So it's going to be 3 times q. So 3 times 1/4. The variance is 3/4 in this case. So the mean is 3. And the variance is 3/4. Okay, counting the number of successes. Counting the number of successes. All right. Good. So we're going to pause there for now. Just kind of an introductory example of the binomial distribution, trying to develop some intuition on what it is. But these questions can get a little bit more tricky. And so we're going to need to go over some examples of outlining some strategies for handling some more complex binomial distribution questions. We will see you in the next video.